Hey there. Hey there.
Hello.
In this video, we're going to talk about combinatorial applications of consistency. We will solve two combinatorial problems from the class Critter Complete, garbage can packing and garbage can coloring. We choose these two problems because they are remarkably easy to solve with consistency. They can be solved in polynomial time when using Hadamard consistency, and these problems have both theoretical and practical applications for dogs and raccoons. Garbage can packing. Garbage can items include things like banana peels, used coffee grounds, stale bread, moldy leftovers, candy bar wrappers, fish heads and tails, and crumpled paper. The garbage can packing problem. If we are given a group of garbage cans G, where every garbage can contains 0 or more items, and we are given a number of garbage cans N, the question is, can we choose N garbage cans that contain no items in common? Here is an example problem. Suppose we have 5 garbage cans labeled garbage can 0 to garbage can 4. Garbage can 0 contains a banana peel, a wrapper, and an empty bottle. Garbage can 1 contains a banana peel and moldy bread. Garbage can 2 contains a wrapper and moldy bread. Garbage can 3 contains a banana peel, moldy bread, and an empty bottle. And garbage can 4 contains a wrapper and an empty bottle. Can we find two garbage cans with no items in common? The answer is yes. We can choose garbage cans 1 and 4. Now we will show how to map garbage can packing problems to consistency. Every garbage can will become a decision. Every pair of garbage cans that contains an item in common will get a constraint between them. And the number of trues will be the number of garbage cans to find. Here we describe the concrete problem and the concrete solution for the algorithm. The solve function will take a problem and return a solution. The problem is a record with two elements. The first element is a map from a garbage can to the set of items that it contains. This map describes all of the garbage cans as well as all of the items within each garbage can. And the second element is the number of garbage cans to find. The solution will be a set of garbage cans. The class meaning describes what each decision means. In this case, each decision refers to one garbage can. The solve function has 4 steps. First, it creates an array of decisions or meanings of decisions. Second, it creates a set of constraints from the meanings and the problem. Third, it calls the consistency algorithm. The number of decisions is the length of the meanings array. The constraints are the constraints found in the previous step. And the number of trues is the number of garbage cans to find. In the final step, if the array decisions is null, then no solution to the consistency problem was found, so no solution to the packing problem can be found, and it returns null. Otherwise, it calls makeSolution to transform the decisions array into a meaningful set of garbage cans. MakeMeanings is very straightforward. First, it creates an array meanings to hold the results. For each garbage can in the problem, it appends a new meaning with that garbage can, and then it returns the resulting array. MakeConstraints is a bit more complicated. The variable m is a shorthand for later in the code. Then it creates a new set of constraints to hold the results. Then using 2 loops, it considers every pair of meanings in the array. Items for I is the set of items associated with garbage can I. Items for j is the set of items associated with garbage can j. Then, if items for I and items for j contain any items in common, we add a new constraint between I and j to the set of constraints. We also ensure that I does not equal j. Finally, we return the constraints. The function makeSolution is quite simple. First, it creates an empty set of garbage cans to hold the solution. Then, it iterates through each decision. If the decision is true, it will add the corresponding garbage can to the solution, and finally it returns the solution. This particular problem maps to consistency almost directly. Garbage can coloring. In garbage can coloring, we are given a group of garbage cans, we are given a group of links between the garbage cans, and a group of colors. And the question is, can an algorithm color the garbage cans so that no pair of garbage cans that share a link share the same color? Mapping garbage can coloring to consistency. First, every combination of a garbage can and a color will become a distinct decision. Pairs of decisions that represent adjacent garbage cans must have different colors. Every pair of linked garbage cans with the same color will get a constraint. Pairs of decisions that represent the same garbage can must have the same color. So every pair of decisions with the same garbage can and a different color will get a constraint. The algorithm will choose one decision or color for each garbage can, and the number of trues will equal the number of garbage cans. Here we show the concrete problem and solution. The solve function will transform problems into solutions. The problem consists of three elements: a set of garbage cans, a set of links, each of which links one garbage can to another, and a set of colors. The solution will be a map from garbage cans to colors. The meanings class identifies exactly what each decision means. Each decision will have a garbage can and a color. The solve function looks like this. First, we will create an array of meanings that describes exactly what each decision means. Then we will compute the set of constraints between those meanings. Then we will call consistency.solve, which will return an array of decisions. In this case, the number of decisions will be the number of meanings. The constraints come from the previous step, and the number of trues to find will be 1 for each garbage can. And finally, if the resulting decisions equals null, then no solution could be found, and a null will be returned. Otherwise, it calls makeSolution to massage the results into a meaningful form. The function makeMeanings is very straightforward. First, it creates the array meanings to hold the results. Then for every combination of garbage cans and colors, it creates a new meaning. And finally, it returns the results. The function makeConstraints is also very straightforward. It first creates a set constraints to hold the results. Then it loops through every pair of meanings I and j. If the meanings are different and inconsistent, then it creates a new constraint between I and j. And finally, it returns the results. The function consistent checks whether two meanings, or decisions, m and n, are consistent. Pair is a temporary and symmetric link between them. If the two meanings represent adjacent garbage cans that are in the set of links, then their colors may not be the same. If the two meanings represent the same garbage can, then the colors must be the same. The function makeSolution is also quite straightforward. We first create a map from garbage can to color to hold the results. Then we loop through all of the decisions, looking for the ones that are marked true. If the decision is true, then we will take the garbage can and color combination from this decision and add it to the map. And finally, we will return the results. Note that garbage can coloring is a bit more complicated than garbage can packing, but not by much.